Hi students, Professor Nugent here. Let's look at the identification of an instrumental variables estimator. Given that our assumptions hold, that is, the covariance between x and the instrument z is not 0, and the covariance between z and the error in the structural equation is 0, we can derive an expression for beta 1. So let's do that. Let's derive an expression for beta 1 and think about the identification for beta 1. We can start with the covariance between the instrument z and y and then plug in the equation for y. So that is equal to the covariance between z, and here we have beta naught plus beta 1 x1 plus u. This is equal to beta 1 covariance z and x plus the covariance between z and u. The covariance between z and beta naught drops out because beta naught is just a parameter, right? And now we have assumed that the covariance between z and u is 0, so this will drop out, so that the covariance between z and y is equal to beta 1 times the covariance between z and x, which we have assumed to not be equal to 0. And now beta 1 is equal to the covariance between z and y divided by the covariance between z and x. Now, given a random sample, we can estimate this expression. So beta 1 hat is then given by the sum from I equals 1 to n of zi minus z bar times yi minus y bar all over the sum from I equals 1 to n of zi minus z bar times xi minus x bar. Applying the law of large numbers, instrumental variables is consistent, and the plim of beta 1 hat is equal to beta 1. In small samples, the instrumental variable estimator is subject to substantial bias, and we will talk about finite sample bias in a later video. Let's spend a minute talking about statistical inference. First and foremost, instrumental variables has an approximate normal distribution. We revise the homoscedasticity assumption so that our expected value of u squared conditional on z is equal to the unconditional variance of u, which is sigma squared. So we're still going to make our homoscedasticity assumption. We will be later able to apply our usual heteroscedasticity methods for an instrumental variables approach. Now the asymptotic variance of beta 1 hat is given by the following. Our asymptotic variance of beta 1 hat. This is sigma squared all over n times sigma squared x times rho xz, where rho xz, that's the correlation coefficient between x and the instrument z. And observe that this asymptotic variance decreases at a rate of 1 over n, and is lower the stronger is the correlation between x and z. Also observe that this is our asymptotic variance, which is in terms of population moments. We want the sample analog, the asymptotic standard error. So the asymptotic standard error is given by sigma squared hat all over the total sums of squares in x times r squared xz, where this is the coefficient of determination in a regression of x on z. Observe that this standard error differs from the OLS standard error by the inclusion of this coefficient of determination. And this coefficient of determination will always be less than 1, which means that the asymptotic standard error for the instrument of variables case will always be larger than OLS. All right, folks. That is it for identification and statistical inference. Stay tuned to the next video. We will discuss the instrument of variables setup.